right? The main important thing is that there's no clock overlap issue. Looks like no, right? Overall, it has no clock overlap issue. Before this, again, I'll ask you, is this a positive or negative trigger edge register? Right? This is just like an exercise. This tells you what is a negative or positive edge trigger register. I already show you this is a master stage, this is a slave stage, right? So it's a master slave flip-flop. The first one is what? Is it transparent high or transparent low?
Transparent low.
Transparent low. I hope you can see it. What you mean is when the clock equals to 0, right? Bar clock equal to 1, then it means this is on because bar clock is connected to CMOS and clock is 0, so this is on. So it is transparent low, right? So let's understand what you mean. When it is on, it means this is just a line. So when you analyze a circuit, you see something very complicated. What you will do is, you know, you're talking about certain clock value. When this is low, means it's high, this is low, then these are just lines. You just connect them with lines. Yes, they have resistor, they have capacitor, but they don't affect the function. We are not testing you the delay at this moment, only the function, right? If they are lines, this is just an inverter. Right, so this logic is such that you build all the pull-up network and pull-down network and gated by the clock, right? So then now you have this transparent load, right? But of course, this we talk about register, you only need the inverter. So if this is transparent low, how about the next one? Is it transparent high or transparent low?
Transparent high.
Thank you. So if I have a transparent low one followed by a transparent high one, what type of register is this? Is this a positive edge trigger or negative edge trigger? Right? To think about this, you think about when you go from low, what happened? When it is low, clock is low, this is transfer from D to X. And then, but this is off, right? This is off. And then when the clock suddenly goes up, this will be on, X will be transferred to Q. And then this is off. Let me still do it one time. I hope you, if you think that I'm too slow, let me know, right? When the clock is 1 or not clock equal to 0, then what does it mean? This is on, but at this time, this is off, right? So at this time, is X copy to Q. And for this one, at this time, D copy to X. So from the overview, you see that, hey, when the clock is low, nothing happened because Q is still Q, D is not affecting Q. But suddenly when the clock becomes high, then X copy to Q, then you have a feeling that, oh, it looks like this is a structure that when the clock goes from low to high, D is copied to Q, right? Is this clear? And because of this, this is transparent. This is what, positive or negative?
This positive edge trigger.
Thank you, right? Let's do this again. When this is the clock, during this time, D go to X. And during this time, X go to D. Then it appears that this is a positive edge trigger. I mean, go to Q. Okay? Very simple, right? Now then let's study. Any questions? Now let's study the clock overlap issue, right? We know that there is clock overlap issue because you have the clock goes in, you to generate the clock bar, you need to go through an inverter. So that causes a delay. So clock bar is always slower than the clock, right? So you draw it, you definitely will draw something like this. Draw the clock first. And then I know the clock bar is going to be slower, and then I know it's going to delay, and it's the clock bar. So it will be like this, right? Okay. So from here, you see that when the clock goes up, the clock bar is still up. This is called 1-1 overlap, as we said earlier. And from here, when the clock goes down, the clock bar is still low. So this is 0-0 overlap. In the last class, we see that if you have 1-1 or 0-0 overlap for certain circuits, you are going to contaminate the data because you suddenly turn on both latch at the same time. And then D is going to affect the Q if the D is changing. Or there can be even black flow if for a certain circuit that you actually use this bistable state, right? So do we have problem in cross CMOS if we have 1-1 or 0-0 overlap, right? So I already give the answer here. No, there's no issue for 0-0 overlap. Why is that? So in order to understand this, you need to draw this circuit and then think about what happened when your clock goes up, okay? So you see that for not goes up, for 0-0 overlap, right? I try to write down my logic. For 0-0 overlap, when does it happen? It happens when clock goes from 1 to 0. So when clock goes from 1 to 0, it means that it means what? The first stage is on, right? It means we try to D is copied to X, right? When clock goes from 1-0, right? We'll go to from 1 and then 0. So when it is 0, I expect this stage to be on and then this stage to be off, right? So ideally, X cannot affect Q, right? When the clock was 1, we copy X to Q. Now it goes to 0. At this stage, we're supposed to turn this one off and then turn this on so D can go to X. But now we have 0 overlap, right? Right? Ideally, it cannot affect Q because M8, M7 should be off. Is this okay? Ideally. Well, if there's no clock overlap, this two should be off because clock becomes 0. So clock bar becomes 1. So this should be off. Is that okay? This is the first step, right? But however, due to 0-0 overlap, M8 is on, right? And also M3 is off. You see that, right? Ideally, we turn on M4 and M3 now and turn off M8 and M7. But because of 0-0 overlap, the clock bar is still 0 at this time. So M8 is on, but M3 is off. So can you tell me how can we affect the Q? To affect Q, right? We already copied the data. how can X affect Q? What are the possibility to affect the Q? How do you change Q? What are the for this given circuit, right? At this state, this is off, this is on. What are the possibility that the Q can get affected? Can you think about this and let me know? So Q can be, for example, if Q is 1, the data was 1 Q, would it be affected by this circuit?
No, Professor. Actually, I think it will be affected by 0 because PMOS can't provide exact 0, right? We use NMOS to conduct correct 0. So during 1, it won't be an issue, but during conducting 0, it will be an issue.
You mean if Q is 0, it will be an issue?
Yes, Professor. If if X is 0, it will be an issue, I'm saying.
If it is 0, then it is an issue. Are you saying that?
Yes, Professor, because
Right.
PMOS can't correctly conduct 0, right?
Because this one will charge up the Q. Is that what I'm trying to say?
Yes, Professor.
Good. Right? The only possibility is Q was 0 and accidentally change to 1 due to M6, M8, and X goes from 1 to 0, right? Let's say originally my data was at 0. And then your X suddenly during this, let me also say this, during overlap, right? During this overlap, I was at 1. And then you suddenly change from 1 to 0. When go to 1 to 0, then this is turned on. And then this one is going to charge me. And then I becomes 1, right? I was at 0. Did I say something wrong? Let's say I was at 0. And this one suddenly changed from 1 to 0 due to some reason, due to the overlap. And then this one will change to 1. Then my data got corrupted. Is this okay? Is this clear? If my Q were already at 1, I really don't care because all you can charge me is just 1. You cannot bring me to 0 because this is off, right? So if my data were at 0, the only possibility is when Q is 0 and you accidentally change Q to 1 because M6 and M8 are on and X go from 1 to 0. Okay? But is this possible? Right? But can, in this situation, can X change from 1 to 0 based on here? How can X change from 1 to 0? It relies on data. If the data change, it might change X, but it's impossible because X was at 1. So no matter how the D change, you cannot change X from 1 to 0 because it is still 1, right? But X can only stay at 1. So as a result, it's impossible to have an issue. It means that even you have 0, 0 overlap, you don't affect my data. I function very well. Once you have this positive edge trigger, you copy Q to here, and then you go down, although you did not turn off this 2 successfully because of 0, 0 overlap, but my data is not going to change. Because if my data were at 1, you can only change 1 to 1. You're not changing me. If my data were at 0, you can change me to 1, but this requires X to change from 1 to 0. But X cannot change from 1 to 0 because X is connected to VDD. Okay, but if X were at 0, then this were at 1 already. So it's not going to get corrupted. So there's no problem with 0, 0 overlap. Right? Maybe a little bit confusing. This year, I spent a lot of time to write this slide. Can you think about that? See if there is any questions? Everything clear? Okay, if it is clear, right, then let's look at 1-1 overlap. This is still say that 1-1 overlap is not an issue, right? So let's draw the clock again. Drawing the clock is very important. So in the exam, try to draw it. And in particular, remember, you need to remember, put the clock bar after it, okay? Switch to the right. Then you can clearly see when it has the 1-1 or 0-0 overlap, right? You cannot just randomly shift it. Here is 1-1 overlap. And you see that 1-1 overlap occurs after positive edge trigger, right? Positive edge, right? No, let me don't say trigger. So after positive edge, ideally what it means after this, ideally we say that we are going to copy X to Q, and at the same time, you are going to turn on M8, M7, and turn off M4 and M3. Is that okay? Ideally, right? When you go to positive edge trigger, let's see, I did something wrong in my cop bar, but no one remind me. This should flip over, right? This one should flip over. What I've just drawn is just a pure shift of clock, right? Okay, right? This is 0-1, 0-1. So at this point, right? For example, you see that I expect this clock bar to be low, so turn off M3, turn off this one. But because of 1-1 overlap, right? M3, which is supposed to be turned on, turn off is on, right? And then M8 supposed to be turned on right here is off because of the 1-1 overlap. Okay, then the question is say, can I affect the data? Now, can you do the same thing? Can you tell me, right? Q can only be affected if what? If it is at what state? How can I change the value of Q, right? Because after the edge trigger, I already copied the data to Q. Now my worry is that I have 1-1 overlap. Will the circuit somehow contaminate my data? How will it contaminate? How can Q be changed? I mean, how would it change based on this circuit?
Q can only be affected if X is 1.
If X is 1 and Q was?
Q is 0.
0.
Is it? 0,
No. Right. I mean, Q becomes 0, but before that, if Q was 0, I don't care, it's affected because it's connected to ground, right? Q is only affected if Q was 1 and becomes 0 due to M5, M7 on, and X goes from 0 to 1 due to this. Make sense? Q only has a problem if it was at 1. If we was at 0, this one can only pull it to 0. Right? It can never go to 1. So no problem. I don't care how messy the circuit is here. If I am at 0, I'm happy. I'm done. No one can corrupt my data. But if Q were at 1, this circuit can corrupt it by bringing this to 0. And how can I bring it to 0? X has to go from 0 to 1. Okay? But again, for the same quota, can X go from 0 to 1? Is it possible for X go from 0 to 1? Are you able to put in a D value so that X go from 0 to 1?
It is not possible.
Not possible, right?
Yeah.
Because, but X cannot, maybe I should say, but there is no D values can make X goes from 0 to 1 because X is connected to ground. The best the D can do is bring X from 1 to 0. And if you bring it from 1 to 0, then it's not going to corrupt this Q. Right? So no problem with 1-1 overlap again. Is this clear? Any questions? Right, so it's a little bit confusing. All you need, but I found the trick is that draw this clock, draw the clock, look at ideal situation, right? Right before the overlap, what happened to the circuit? It can be this circuit, it can be those circuits we discussed in the last lecture, it can be new circuits in the exam. And then try to see if there's no overlap, what happened? For example, in this case, if there's no overlap, we say that this is cut off, Q is safe, right? Because it's cut off. No one can affect Q. But now because of overlap, M7 is on. Okay, M7 is on. But even it's on, if you want to change Q, you can only change it from 1 to 0 because of this connection. You can never change it from 0 to 1. So if you were at 0, no corruption. If at 1, there's a possibility. But in order to make this from 1 to 0, it means I need to make X from 0 to 1 to turn on 5. But then you find that for X itself, it cannot go from 1 to 0, 0 to 1, because it's connected to ground. Then you say that no problem, no corruption. Okay, so no problem with 1-1 overlap. However, this is just a superficial thing. If we think deeper, actually there is a problem with 1-1 overlap. But this happened right after the overlap. So what is that? Let me draw the clock again, right? This is the clock. And this is the clock bar. Okay? And the overlap is here. Okay, this is 1-1 overlap. Now we say that no problem during 1-1 overlap, right? We already showed that. See previous slide. But right after what happened? Right after clock bar becomes 0, that is okay, right? It becomes, that's what we want. And then when clock bar becomes 0, M8 turn on, M3 turned off. Okay, so that is what happened, right? right after the clock, this is M8. This is 2. Right after that, this is off. Okay? So looks okay, right? But the problem is this. If X was corrupted during 1-1 overlap, right? Remember that this is during 1-1 overlap. We say that, yeah, you can corrupt my X from 1 to 0. Okay, I don't care because this is not going to affect me. You go to 0, my Q is still okay. But if you were corrupted during 1 overlap, that X was 1 and it becomes 0 during, right? This is very important. It's during the overlap. Okay, then right after 1-1 overlap, right after, right? Because it becomes 0, it will turn on M6 and charge Q from 0 to 1. There's some problem with this one. You see what I mean? If X was corrupted during the 1-1 overlap, X will go from 1 to 0. It was at 1, right? It was at 1, so I expect Q to be 0, right? But because now you change from 1 to 0, once after the overlap, it will turn on M6 and charge Q from 0 to 1, right? Then you corrupt the Q. So 1-1 overlap is a problem, but it's not during the overlap. It's once after the overlap, then it has effect to charge this from 0 to 1. Remember here, we keep seeing that we don't care because the Q, right? The only way I can turn off to affect the Q is when discharge it from 1 to 0. If this is 0, no problem. But the problem is here. If this were 0, right? Then due to this overlap, right after overlap, you will charge 0 to 1. Is this okay? Any questions? How about let's think for 1 minute, right? And let me know. Everything okay? Now, if that is the case, how can we solve this problem? I'm not asking to solve the circuit. It's very simple. And I already give you this. It means that we cannot, during the 1-1 overlap, you really don't change D. If you don't change D, then I don't have this problem. So what should be the whole time? Can someone tell me? What's the requirement? What's the whole time requirement for this circuit? Whole time, again, is what? Is that when my clock goes up, your data better hold for stable for some time so that I can copy it successfully. So what should be the hold time for this case? Anyone try to guess? So we just say that, right? I try not to give you the answer. I try to think. I just say that during the 1-1 overlap, there's no problem. But once after the 1-1 overlap, the X can contaminate the Q. So we need to hold this X not changing. It also means we need to make D not changing for certain time, right? So how long D should be constant so that it won't affect the Q. And that is the whole time. Whole time basically said after the clock goes up, you see here, the clock goes up, right? This clock goes up, it means you copy the data to Q, right? But then due to 1-1 overlap, if you change the data during 1-1 overlap, then we still can contaminate the output. So you need to be constant during 1-1 overlap. So what is the whole time for this circuit? How long should I keep the data to be constant after this positive edge trigger?
Should it be greater than the overlap time for 1-1?
Yes, that's what I'm asking for. Maybe too easy. You don't want to answer, right? So your whole time need to be larger than the time of 1-1 overlap. Okay, so in your circuit, when you give this circuit to someone else, you say, no need to understand what I'm doing. This is a positive edge trigger register, but I require you to have the data hold time larger than this. Let's say 1-1 overlap time is 1 nanosecond. Larger than 1 nanosecond. Otherwise, I cannot guarantee my register will work for your purpose. Okay? And now you see that this overlap really depends dynamically because at different places of the circuit, you actually have different overlap. We're going to study this called the cross, not cross skew, but it's kind of related. Kind of related.
So, Professor,
Yeah.
if we wanted to define T11 overlap for this schematic,
Yeah.
how would we do that? Like, that would be the delays, that would be the sum of the delays of like which transistors, like in which path?
It is the delay between clock and clock bar, right? What is the delay between them based on this?
So just the buffer. So
Yep.
T hold, or I mean
1-1
T-
overlap.
yeah, for the buffer, right?
Yeah, exactly. And if you to be more specific, right? This is talking about the clock goes up. For 1-1 overlap is when the clock goes up. It means this one go down. So this is TPHL, right? It's just the delay of your inverter, TPHL for 1-1 overlap. For 0-0 overlap is TPLH. Make sense? Because this is the output. It takes time to go from high to low. This is the delay, right? So this is like TPHL. One, I would say that is like TPHL. 0-0 is like TPLH. Make sense?
Yeah, that makes sense.
Yeah. So you see that all you learned before are all relevant, right? TPHL, TPLH. Okay, any more questions? If no, let's move to, although this one I spent a lot of time, but these are very important. I feel that you need to know the basics, right? Now then, let's work on more. I have so-called dual edge trigger register. What I'm doing here is so complicated, but just break it down. I have two registers, one on top, one on bottom. On the top one, you already learned it. Is it a positive edge trigger register or negative? Maybe you cannot see it right away, but this is still the master-slave flip-flop, right? So the first stage, what do we call it? Is it transparent high or transparent low?
So for those M1 to M4 you're talking about, that should be a positive.
This is a latch, right? So it's transparent high or transparent low?
When low,
Transparent high.
yeah, I would agree.
Yes, and that's why you say positive, but I want to the exact name, right? So high. That's why what you mean by positive, I guess. So this is transparent high. The next one, you swap the clock, so it's transparent low. So on the top, what type of register is this? Positive or negative edge trigger? You see that when it is high, you copy to X. When it is low, you copy to Q. So you see that when you go from high to low, you suddenly copy the data, right? So this is
Negative edge trigger.
negative. Thank you. Now here is just like what we usually do in the schematic. N1 is here, N2 is here. You just copy. And you see that the clock are swapped, and this is just a positive edge trigger. Okay? Right? So no problem, right? So what are we doing here? You basically, that is what you are doing. I have data coming in. You goes to two register, DQ. And then on the top is negative trigger. So I put a not circle here. DQ. At the bottom, right? This is clock. Okay. And then you combine the Q here. Okay, this is Q. So basically, it's going to copy the data, whether it is positive or negative. When it goes up, it copy from here. I mean, opposite. It goes from the bottom, right? When it goes down, it copy from here. Is this okay? So by doing this, we actually copy the data 2 times in every clock. Okay, so here, if I call this D1, this, I mean, the best is maybe call this D1. D2, right? So when it goes up, then the Q equals to D2. When it goes down, the Q equals to D1. Okay, so this is so-called dual edge register. And why they say it's save power? Because you can reduce VDD for lower frequency. It will save power. And this is kind of expected because you double the hardware. It's just like if you have 2 ALU, you have 2 adder, you can do it slowly to have the same throughput, and then you save power. This is the same logic. Okay, any questions?
Using a dual edge, this is gonna be slower, or are we gonna
slower, but you have the same throughput because you are for example, you can double the reduce the frequency to half, right? And you still copy it 2 times. For example, it was 1 gigahertz. Now you do 500 megahertz. In the past, every one clock cycle, let's say you copy one data, so you have 1 10 to the power 9 data copy every second. Now you reduce to 500 megahertz. You copy 2 times in every clock, so you still have 1 to 10 to the power 9 data copy. Make sense?
Yes, Professor.
Okay. Now, then we also have something called true single phase clock register. Here you don't have overlap issue, right? The clock CMOS still have a little bit clock overlap issue. Here there will be no clock overlap issue. Okay, so on the left is the negative latch. On the right is the positive latch. Okay, so for example, when clock equals to 0, when clock is 0, this is on, this is on, this off, this is off, right? If we make them together, it becomes when we connect, right? So that becomes a positive edge trigger register, right? Because on the left is the negative latch transparent low. This is positive latch transparent high. Okay. Now, if the clock becomes 1, then this is off, this is off, this on, and this on. Can someone tell me why there's no overlapping issue? By the way.
Clock is the same for all of them.
Well, very good. There's no clock bar. Then where's the overlap? Only have a single clock, right? So no overlapping issue, right? So you can see that when it is 0, this turn on, then it pass to here. When it's 1, turn on, pass to here. The only problem is you never get perfect. There's always some drawback, right? Engineering. That's what we learn, I think, from engineering the most, is that no perfect solution, always have a trade-off. The trade-off is that when this is off, okay, and for example, right, let's say it is off, and for example, let's say we actually store 0, okay, so it can be this. Let's say this is 0, right, and then it means this is 1, this is 0. So in this case, this is also off. Okay, this is on, this is off. In this case, this guy, right? This guy during clock equal to 0 is floating, right? When the data is 0 here, and then you have the clock that is 0, this is off, and this is off, then this is 0, right? Then you will be susceptible to noise. Then your noise margin reduce. You remember all those coupling. We will talk more about this on Wednesday. But is this okay? True single phase clock register, no clock overlap issue. No need to worry about hold time. Okay. If no question, then let's move forward. So how can we increase the speed of the clock, of the calculation? We